Hello and welcome. Hello, hello. Okay, all right. I had not seen your message yet. Let's see if it's in my inbox. All right. Oh, so it's an actual email, not a message. Okay, I'll look for that because I assume it's an actual email because I didn't see it in my Canvas inbox. Okay, there it is. Handout 5. All right. Cool. So let's look at. Yep. So you're just interested in number 2 by the looks of it. I could see why. Number 1 was pretty straightforward. And hi to it. How's it going? All right, so let's talk about your solution to number 2 from homework 5, from handout 5. All right. I'm going to over here. All right. Handout 5. There it is. Okay. Looks good. Okay. So looking at part A, I was asked for the velocity at the particular point. All right. And so let's look at your function. So you got negative 4.1. Yeah, that's basically what I got. I got 4.12, but that's very sensitive to rounding. And then what did you get for your angular frequency? I'm just looking over your notes here. All right. So let's see, for your angular frequency, I see it up here somewhere. Okay. Well, that's your period. Okay. Where's your... But that, oh, I see. Maybe you expressed the function. Yeah, you did. It looks like you, yeah, which makes sense, you know. It totally makes sense to do it that way. Yeah, you express your function with the 2 pi t over t. Oh, and then you took the derivative. Okay, that's fine. Makes a lot of sense. So let's see. Did you get the same? Yep. So your value is fine. Oh, thank you. Yeah, it gets so long. So what I will say, and I won't walk you down for this at all, but it's just something to be aware of, that sine functions are really, really sensitive to rounding. So if you don't round at all, if you like save your values in your calculator and then use them, then you will get a slightly different number. So for example, you got negative 3.93 as your instantaneous velocity at that time. But if you hadn't rounded, you would have got negative 3.88. So it's a small difference, but it definitely it's. I mean, I'm curious. Oh, I have my other calculator downstairs. Hopefully this one has batteries. Yes. Okay. Oh, I forgot how to use this one. Where's the home button? Oh, there it is. Okay. Okay. I hadn't used this one for a while. There. Okay. So I'm just going to do 3.9366 minus 3.88 and divided by 3.88. Yep, times 100. So it ends up being a 1.5% error between the number that you got, Kyle, and the value without any intermediate rounding. So it's subtle, but it does matter, but you won't lose points for it. Okay. And then let me circle around to part B. If you'll hold tight for just a second, I want to look at Tuit's question. Can you go into number 2 on handout 5 more in depth? Okay. All right. Yeah, absolutely. So that's what I'm talking about right now. Kyle sent over his work for problem 2 from the homework. So that's what I'm talking about right now. And you say that canceled lab 15. Jason, did you see my weekly look ahead video? I discussed the fact that we're only doing 1 lab during these final 2 weeks. Where there's so much material. The last thing we need is 2 extra labs. So I did discuss that in the weekly look ahead video. And yeah, basically we just have 1 lab between now and the final. So you're basically right on that in that respect. We have 1 lab on pendulums. Okay. I hope that answers your question. So yeah, we're having one less lab. You're absolutely right that there's no lab covering the material for gravitation. I actually have a handout that's kind of that I use sometimes, but it's I think that we want to. I would rather we just focus on a few problems rather than spending a bunch of time going into a bunch of in-depth problems, and just so that it's not an overwhelming amount of information in what is already such a busy couple weeks. Okay, so back to handout 5 for physics 37, homework problem 2. So I do want to ask one clarifying question to it. You said you had no idea how to do it. Any particular part? Did you have no idea how to do part A or part B or part C? What was it? I'm gonna grab a tissue. Excuse me. But again, which part was giving you issues on handout 5? Okay. So it's very, very similar to the example that I showed in the lecture notes. So in the lecture video, I should say. So in the video, I go over example 1. I'm just opening up both my versions. Okay. So in my video, I go over what is example 1. And there it's the same sort of idea. You can see that there's a lot of similarities. The system is different. In one case, it's a pendulum. In another case, it's a spring. But they both follow all the same rules. So the idea is that in what you need to do is you need to use the equations of motion for the oscillator to find a time and then to plug that time into the appropriate equation of motion, which in both cases, I believe you're going to plug it into the angular velocity. The velocity of the mass, yeah. Okay, so you can also solve part A of handout 5 homework problem 2. You can also solve it using conservation of energy. Because there is no actual time, so you don't need the time function. So you can do it that way. You can actually solve part A with conservation of energy. You cannot solve part B with conservation of energy because it is asked at a particular time. So you do need the actual time-dependent, the time-dependent position functions, velocity functions for, for part B. But that said, you can definitely do part A with energy. Mm-hmm. I mean, there's, okay, so where do I want to start with this? Did you attend the class meeting today at noon? Just to kind of know if there's any crossover. Did you make it to today's class meeting for Physics 37 at noon? Okay. All right. But no, that's okay. I want to see, because we talked about this one a bit, as well as the current week material as well. So let me kind of start then with like the initial idea. Okay. So I'll kind of like work through the steps. Okay. So let's go. I got some notes over here. Let me make a duplicate of it. Okay. Okay. So for part A, the idea is you have the position function. It's a spring, so it'd be x equals a cosine omega t. Okay. All right. So that's your time-dependent position function for a spring oscillator. Okay. Then you in part A, we're also asked about velocity, so you're going to want the velocity function as well. So then velocity is negative omega a sine of omega t, and let me make that clear that that's the first derivative. Okay. And I do want you to show that it is the derivative. So like in physics 35, for example, I just give you that equation and I say, okay, here's the velocity equation. Take this as a equation to memorize. Here, however, we can always derive the equation because we know it's just the first time derivative of the position equation. Okay. So then what you want to do is you want to solve the position equation for t and then plug the value of t into the velocity equation. Okay, so that's the process. You would use the upper equation, the a equals a cosine omega t. You would solve that for t, obviously by isolating t using the fact that you have to take an inverse trig function. Then once you have that value of t, you will then plug it into your velocity equation to get your velocity. Okay? But I have a concept question for you. So considering that the position function for a spring oscillator is described as cosine, okay? And that's a choice, but it's a choice that we stick with. All right? So given that we describe the position function as cosine, what would be the sign of the velocity function after 5/7 of a period? Okay? So maybe put that in the text, the chat. So given that the position function is cosine, what would be the sign of the value of velocity after 5/7 of a period of oscillation. Okay, because you should be able to answer this question, because you have to have a quick ability to like come up with the correct sign in order to be able to check your work. You have to be able to think about where you are on that sine curve and be able to relate that back. Otherwise, these problems just become sort of meaningless. Okay, so I really want to discuss how we would conceptually answer this question. Given that the position function is cosine, then what would be the sine of the value of the velocity after 5/7 of a period of oscillation? Okay, because let's see, so 5/7, it's 0.7, so it's less. Okay, it's less than it's over a half. Okay, it's over a half, but it hasn't, it's yeah. Okay, yeah, so after 5/7, yes, positive or negative, exactly. Which is going to relate to part B, kind of, right? Part B, we're also interested in the acceleration, but I figured we'd start with the sign in order to get you thinking. Exactly. Yep. Because for half a period, it's negative, right? Because it starts over here in the positive, it's moving in the negative direction for half a period, then it reaches a point where it stops, and then for the next half period, it moves in the positive direction. Exactly. Yep. And so then every half period, it's going to go back and forth between negative and positive. Good. All right. Excellent. Okay. So then in part B, I asked you for the acceleration when the instantaneous time is 5/7 of a period. So what would be the sign of the acceleration after 5/7 of a period? Okay, because where do we win? That's a half, and 5/7 is more. 5/7 is 0.71, right? So it's greater than a half, but less than 3/4. Right. So we've gone this way. We're moving back over here. What would be the sign of acceleration? At 5/7 of a period of oscillation. We put, sometimes it's like have a record of this in chat. Right, and then just put the next question up. What would be the sign of acceleration after 5/7 of a period? Okay, close but no. Okay, because it wouldn't be just barely negative. No, it would definitely no, not negative, which means it's going to be positive. But why? I'm going to draw a picture. Trying to think if I need position. I can get away with just doing velocity and acceleration. All right. By 0.04, do you mean 0.04 as an actual value of acceleration, or do you mean like 0.04 like a fraction of a period or something? I'm not sure what you mean by 0.04. Give me some units. That'll answer my question. No, that would not be correct. Okay, but we can figure out why. Trust me, like the graphical way of thinking about this is so crucial. Because first of all, we could just literally solve it with graphs. We could actually plot this out and just do like intercepts and whatnot. But it kind of makes sense to solve it algebraically. But the understanding, I mean, I draw the graphs when I do these problems because I don't think there's any other good way to visualize this. It's not like a free body diagram where you can you're drawing the vector, so you kind of intuitively seeing it. With the oscillations, it's invisible to the mind's eye unless you have, practice drawing it. You have to have that in order to start to learn this stuff. Okay, so I just want to show you the velocity and acceleration. Okay, so here are the velocity and acceleration functions. Okay, these are the typical ones. This would be the velocity and acceleration functions of an oscillator with no phase angle. Okay, because remember, the phase angle, and I discussed this in the lecture video, the phase angle is determined entirely by the initial conditions of the system. That means that if the initial conditions are the typical assumed initial conditions, then this is what the velocity and acceleration look like. Okay, full stop. Now, with that in mind, let's think about what a value of 5/7 of a period looks like, okay? Because what is 5/7 of a period? 5/7 of a period is 0.7143 periods, okay? So 5/7 of a period is 0.714 of a period, okay? Okay, because I just like to see it like that because then I can compare it to 0.75, right? Okay, so I'm going to draw some values on both these graphs so we can clearly see some key ideas here. Okay, so we have, and we can focus on the acceleration one. Okay, so we've got, I'm drawing the value which is 1/4 of a period. All right, so this would be 0.25 t. Then I'm drawing the one that is half a period, 0.5 t. Then one that is 3/4 of a period, 0.75. And then finally a full period, t. Okay? See, I've drawn those along the horizontal axis, the time axis. Okay. So, okay. So given that information, what do you now know must be the sign of the acceleration? Where it would be, I won't make you answer it again because you already kind of, I think we already know. It would be between 0.5 and 0.75, okay? It would be closer to the 0.75. So 0.71, let's put in red. 0.71 would be somewhere right around here. 0.71 t. So that would correspond to a value of acceleration. That is that value right here, okay? So then we know that at 0.71 t, our acceleration would be right at the point that I drew on the curve. And then I drew the dotted horizontal line to show the value the vertical value of that point, which would be the value of the instantaneous acceleration of the spring oscillator. Okay, so now we know it would be positive because we're at a point in the oscillation where the acceleration is still pointing in the positive direction because what's happened is the spring started out here. Here's equilibrium, okay? This represents maximum extension. This represents maximum compression. When we release the spring, it's going to travel through equilibrium at 1/4 of a period. Then it's going to travel to maximum compression, at which point it's been 1/2 of a period. Then it will get returned to equilibrium at 3/4 of a period, finally returning to where it started after one complete period. The velocity over that repeating process will be negative for the first half period because it's moving to the left, my left. Then it's going to be positive for the next half period because it's moving to my right. The acceleration, on the other hand, is going to be initially, the acceleration is going to be negative because it's going to be speeding up the mass in the negative direction. So the acceleration will be negative for the first quarter period. But then the acceleration will become positive because now you have a negative velocity, but you know that the mass will be slowing down. So the acceleration is negative for the next quarter period, leading up to 1/2 of a period. Now the acceleration is going to actually be positive because it's going to be in the same direction as the positive velocity, speeding the block back up in the direction of extension. And so you're going to have positive acceleration for the next quarter period, which leads us to 3/4 of a period since we started. But now what's going to happen? Well, the block is going to have to slow down. So now for the final quarter of a period, the acceleration will be negative yet again. End of story, okay? So where are we in this problem? We're in the third part where, acceleration was negative, positive, okay? Positive again, and we're still there. We're still in the segment where it's positive. We're close to the point where it's going to be momentarily zero because the acceleration is momentarily zero every time the block passes through equilibrium. But of course it's zero because Newton's second law says it must be zero. Okay, but we're still in the positive part. Now that said, I got another question for you. What is the magnitude of acceleration of this system? Okay, and by magnitude, I actually meant to say amplitude. So what is the amplitude of acceleration of this system? In other words, what is the maximum acceleration that this system achieves? So what is the amplitude of acceleration of this system? Okay, let me check. So we've got, the angular frequency, let's find the angular frequency first. So the angular frequency would be, the square root. So we're going to do, I'm just going to do the, the square root of k over m. Is that right? Just draw a blank. Let's see. Yep, yeah, of course it's k over m. Yeah, because the units work out. Okay, so square root of k over m. K is given as 510 newtons per meter. The mass is 11 kilograms. All right, and then raise that to the 1/2 power because I don't know what the square root function is. All right, so we get an angular frequency of 6.81 radians per second. Okay, so then the amplitude of acceleration will be the angular frequency squared times the displacement amplitude. And so I'm going to square the value that I got. Okay, so let's square this and then multiply it by the amplitude, which is 60.5 centimeters or 0.605 meters. Okay, so no, it is not 0.5, not even close. It is much, much bigger than that. So try again. What is the amplitude of acceleration of the system? And if you want a hint, I can give you a hint. And if anyone else is here in the office hours that has other questions and is just waiting, we can go back and forth. But if you're curious about what we're talking about, so like, for example, if you're in Physics 40, this is the stuff that we're literally going to be covering next week. So this would be very relevant. Although I'll start posting the lectures as soon as today. Yeah, sure. Okay. So I want to check your part B. I honestly forgot. Your part B is correct, Kyle. And then I noticed that you didn't solve part C. Do you want to talk about part C? But your part B is correct. No, it's fine. It's my fault. I actually meant to circle back around. I just got excited. So yeah, as far as part C, and I'm almost to the point where I'm going to talk about that with Tuid, right? Because we're kind of finishing up talking about part B or getting there. But for part C, the key idea is to find the phase angle. All right. So let me kind of let's read over what's going on. So let me make sure I have the right thing in front of me. I don't want to show you the solution. There we go. Okay. So it says in part C, if the same spring instead started at x equals negative 2a at t equals 0, that's important, what would be the new position function, velocity function, and acceleration function? So the only thing that would be different in part C as compared to, say, part A's or B, I don't know if I said that right, but anyway, so the only thing that would be different about part C is there would be a phase angle. Okay, and you know, I will go over it here, but I highly recommend that you check out the video. And maybe you have, and maybe it just didn't like make sense to you. But I definitely talk about that quite a bit in the video. Like, how do you find it? How do you find a phase angle? And the simple summary, at least the succinct summary, it's not necessarily a simple idea, but the brief summary is that a phase angle is determined entirely by the initial conditions of the oscillating system. That is in stark contrast to the angular frequency, which isn't affected at all by the initial conditions of the system, but instead is determined entirely by the physical parameters of the system. So there's a lot of kind of jargon terms in there, but that's it. That's the idea. One of them, the angular frequency, is all about the physicality of the system. Like, what is it made of? You know, how long is it? How big is it? How much mass does it have? The other is almost purely mathematical, the phase angle. The phase angle is just about, you know, where does your clock start? Okay. So we were talking about this in the class meeting. That's the term I'm looking for. We're talking about this in the class meeting today, and I want to show you the notes that I was showing then. Okay, so I'm gonna hold them up. This would be for part C, to be clear. Let me highlight that for part C. There. Okay, so this is for part C of the homework problem. Okay. So what I'm showing here is that in part C, we're told that the amplitude starts at a value of negative 2a over 5. Well, look what I've done here. Look at the graph that I drew of x versus time. In that graph, you can see that I took a cosine function and I essentially shifted it to my left. Okay? And when I did that, that is the actual representation of the phase angle. That value, which is drawn in orange, that is the phase angle. Okay, that's the idea of shifting it in that direction. That's so your new position functions, velocity functions, and acceleration functions will all have a value which is equal to that lateral shift, that horizontal shift of the cosine function. So what you need to do is you need to find out, like, well, how do you solve for that, right? How do you actually find, what angle that is? Well, you can find it by just thinking, okay, well, you need to find out how long does it take to reach 5/7 or 2/5 of an amplitude. So you can find out the time it takes to reach 2/5 of an amplitude. And then once you have that time, you can take that time as a fraction of the period. and then that will actually give you a fraction. Then you can multiply that fraction by 2 pi, and then it will give you the phase angle on a fundamental level. Okay, because I mean that's what's happening. The other way to do it is to just set up the position function and just plug in your value and then just algebraically solve it. And I'm going to show you the way I did it for the problem, the example problem, just like I showed it in the video. So let me go to that one. Okay. So very similar. The only thing here is that all the amplitudes are represented by theta max because they're angular amplitudes as opposed to physical amplitudes or distance amplitudes like for the spring. But look, I say that the only difference here is that the phase angle set by the initial, I'm trying to read it backwards, by the way, like a reflected in a mirror, set by the initial conditions of the simple harmonic oscillator. All right. So when I do that, then I say at t equals 0, theta equals -5/9 theta max, because that's what we were told. Just like you're told that it's going to equal -2/5 of A. Okay. But A and theta max are the same. Okay. So look what I do. I set it up. Okay. And then I solve for the phase angle. Look at that. Because I know that that's going to occur at t equals 0. And my function, right? The definition of an oscillator. Look at the function from the key formulas. It's x of t, the first spring at least, equals a cosine omega t plus phi. So then what form does the function take when t equals 0? What is, what does, if t equals 0, what does the position function become? So you tell me that. What, type in the chat what the position function would become when t equals 0. Because I want to make sure we're on the same page and we understand that idea. No, what would the position function look like at t equals 0 in a general sense, right? If this is the general position function, x of t, so x as a function of t equals a cosine omega t plus phi, what would that function look like when t equals 0? Is that someone at the door? Yep. Oh, yeah. All right. There's a kid at the door asking my daughter to come out and play, but she's not home right now. Okay. So I'll talk about it. I wanted to see kind of how we stood on the idea. So let's think about it. Okay. So we have a position function. Okay, I'm gonna get a blank page. Okay. So then we'll start with the definition of the oscillator. I'm making a big deal about this stuff because these ideas of like how you describe an oscillator, it's just so fundamental. All right. I mean, and you can't just power through this stuff. You have to understand the basics. Okay. So, all right. So, okay. So then this is the definition of the position function. Okay. And my question was, what is x of t, the position function, when t equals 0? Okay, what form does it take? Okay, so what does the function look like when t equals 0? Okay, that's what I asked. Then that's what we do. We take the function, we plug in t equals 0. Okay, I'm really showing every step here. I also show it in the video. Okay, so if you plug in t equals 0, look what happens. Okay, your t becomes 0 because it's a function after all. Well, what's omega, the angular frequency, times 0? Well, you guessed it, it's 0, which means your function now, evaluated at 0, just becomes cosine of phi. See? Okay, and I can't stress it enough. That is always true. I'll get right to you, Brian. That is always true. There's no exception to that. That's true for any oscillator, whether the phase angle is 0 or not. And I'm going to show why it's 0 a lot of the time. But that's always true. Okay. Okay, Brian sent okay. We're talking about handout 5 right now. So I'll finish what I'm saying and then I'll circle around. So stick around for 5 minutes and then I will check your work, Brian. Okay. I'll keep it at 5 minutes, I promise. Okay. So then let's think about this. Okay. So for a lot of oscillating systems, what is the initial position? Okay. So and I'm gonna say this the way that I tend to say it, just to see if we're understanding if we have a common language here. For a typical oscillator, what is the x value of initial position? For a typical oscillator, what value does x take at t equals 0? And you can just tell me what you think is your best guess. Just what sounds right, what feels right. For a typical oscillator, what value does x take at t equals 0? No, because it wouldn't be a cosine, although you're close. It would just be a. Because it's cosine of what, right? Cosine on itself doesn't mean anything. If you don't take cosine of an angle, it's meaningless. So it's just a. So for a typical oscillator, x equals a at t equals 0. Okay? 0 seconds. Okay? Because a typical oscillator starts at full amplitude. You pull the spring and you let it go. Okay. So what would the phase angle be for a typical oscillator? Okay. And then I'll go check Brian's work. This is the last thing I want answered. Okay. So for a typical oscillator, which x equals a for t equals 0 would be the value of the phase angle. And while you're thinking about that, I'll at least load up the work. All right, cool. All right, so we'll circle back around to my question about the phase angle. Couple things first. To it, you're right, except you called it angular velocity, and it's angular acceleration. And it's also not actually, and it's actually not angular anything. It's translational acceleration because it's a spring. Yep. Yeah. It's just amplitude. Exactly. And just acceleration. It's plain old acceleration. Good. Okay. So you got that, and that's the correct value. Awesome. Very, very good. Good. Because it's omega squared times a. Okay. So that's wonderful. Thank you. The other thing is I wanted to tell you, Brian, that you got the right answer for part B, but you did not get the correct answer for part A. Your answer for part A is slightly off. I'm not sure what happened because I don't see your work or anything, but you got the right answer for B, so that's good, but something went wrong with A. Okay? And then Kyle got the right answer for A, so you can talk to Kyle. Okay, and then I'm guessing that you didn't attempt C. Yeah, it might just be like a little calculator error or something. Yeah, I'm not sure what would cause that. But yeah, just double check it. And just like I was telling Tuit earlier, that the method for part A is you solve the position equation for T, and then plug in the value of T into the velocity equation, which I assume you did because you got a value that's in the right part of the oscillation because you got a negative value. It's just that your negative value is a little too small. So I'm not sure what happened there. But it's so close. Yeah, and I haven't attempted part C yet. Okay. Well, we're talking about the idea behind part C right now. Okay. So, but we have to be able to answer this question. Okay. Really, I don't think your phase angles will never make sense if we can't answer this question. And if we can't answer this question, then I promise you it'll be like the floodgates opened and it will all make sense. So here it is. For a typical oscillator in which x equals a at t equals 0, what is the value of the phase angle? And the phase angle is phi, by the way. That's the name of it. Take a minute and think about it. Yes, it's 0. It's 0. Okay, thank you. And I just wanted, yes, good. Okay, let me show you why, and you'll be like, okay, it will make sense. Okay, because it's a function, right? Okay, so for x to be A, that would be like setting A equal to A cosine phi. Okay. Okay, because this is what we're saying. We're saying a typical oscillator at t equals 0, its position is its amplitude, right? Okay, that's what we're saying. That's the typical oscillator. And then the position is also equal to, at t equals 0, A cosine of phi. So then we can say, thus A equals A cosine of phi. Okay. So hopefully you can see that has to be true, right? Okay. So then we just solve for phi. Okay. So to do that, we divide both sides by A, which means they both just become 1. So then we'd have cosine of phi equals 1, right? Okay. And then we're just going to solve for phi. So then phi would be cosine inverse of 1. What's cosine inverse of 1? You plug in your calculator. What is cosine inverse of 1? Exactly. That's where the 0 comes from. Okay? It is 0 radians. And that is the reason why, for many typical oscillators, we can ignore the phase angle, because it's just 0. Because the system started at x equals A. The system started at full positive amplitude. Okay. But what happens when it doesn't start at full positive amplitude? Like in the homework problem, and like in the example that I demonstrated in the lecture. Okay. Well, in that case, we need to solve for the new phase angle. So in the case of the homework, part C, we're told that the initial value of x is negative 2/5 of A. Okay, so that would be our value of x. So we write negative 2/5 A, and then that would equal A cosine, okay? Yeah. Exactly. You got it. You got it, Brian. See? And then you'd solve for phi. You'd cancel out the A's. Yeah, but Brian got it. And so then you'd find that phi is just cosine inverse of negative 2/5. Okay? Just like that. And that would be the only difference that you would have to make to your position function, your velocity function, and your acceleration function. Is they just now have a phase angle, and you would just show that. And it's just like in what I showed in the lecture, when you solved for different values. See, I have a position function, which is the top one inside the box. The box is the 3 functions. I've got the velocity function, which is the middle one, and the acceleration function is the bottom one. And in each of those, you can see there's a non-zero phase angle. And that's what I want. I want you to write out the full function and then just give me that, show, which will clearly show that you got the right phase angle. Now, we're almost done. We're so close, okay? Brian's absolutely right. You just take cosine inverse of -2/5. But you still have one last step. Because when you do the inverse function, your calculator is going to give you an answer. But you can't quite trust the answer because you actually don't know if it's negative or positive. Because the angle that you get, it could be either one. You don't know. Okay? You don't know which one it is. And so you have to figure out the sign of the phase angle, because the method that I've just described will work, okay? But it will only give you the value of the phase angle. It's not going to tell you if it's negative or positive. All right? So in the lecture video, I talk about the way to do it is to consider velocity. You plug the phase angle into the velocity, and then you figure out either graphically or just like visualizing the phases of the oscillation. You figure out whether the velocity needs to be negative or positive, because the phase angle will give you the correct sign of velocity if it's the right sign, and that's SIGN. The other, but look at the picture I drew, right? This is the same picture I drew in today's class meeting. So this really is a fairly reasonable representation of the phase angle, okay? So looking at that phase angle, that will be necessary, however many radians it is, to shift the graph to the left so that at t equals 0, it has a value of -2/5 amplitude. What would be the velocity, the initial velocity at t equals 0? And remember that velocity is the instantaneous tangent line. So looking at the graph that I have here, the x versus t graph, what would be the initial velocity of the oscillator given the phase angle in part C of the homework problem? What would be the sign, not the value, but what would be the sign of the initial velocity? Would it be negative or positive? I'll keep holding it up. What would be the sign, negative or positive? Yes, exactly. So if you plug in a phase angle that is negative into the velocity equation, will you get a negative velocity or a positive velocity? Because you're both absolutely right. Tuid and Kyle, you're right. The initial velocity will be negative. But does that mean that the phase angle is negative or positive? Because remember, the velocity function is negative sine. So if I plug in a negative into a sine function, do I get a negative or a positive? And if I plug a positive value into a sine function, now, of course, this is a positive value between 0 and pi over 2, if that helps. I think you're all thinking about it. I'm gonna help clarify the question because we're so close. Because then we'll know it, right? We have its value, and this will tell us whether it's going to be a positive phase angle or negative. Okay. So yeah, so are you saying negative in that the phase angle needs to be negative, or that if I plug in a negative into a sine function, I get a negative? I think you're answering that question. Okay. So yes, if I plug in negative, so just here, we'll write it out, right? So if I take sine of negative phi, that's the same as negative sine of phi. This is something you probably remember from a trig class, right? Buried in the back of your head somewhere, right? So sine of negative phi is negative sine of phi. So if I plug in a negative phase angle into a sine function, then it will become negative. Okay? Okay, but then the definition of velocity for an oscillator is negative omega A sine of omega t plus phi. Okay? Okay, there's the definition of the velocity. But here, t equals 0, so we don't need to worry about this part. Okay, so then our initial velocity is just going to be negative omega A, I said the two words as one, of phi. Okay, so that would be my initial velocity, is negative omega A sine of phi. Okay, every time. Okay, and we've got the value of the phase angle, and we want to make sure we get a negative. So that means the phase angle must be nope, the other one. It's not negative. The phase angle must be positive, because a positive phase angle plugged into a negative sine function will give us a negative initial velocity. And that's what we need. Okay? So anytime your initial velocity is negative, your phase angle will be positive. Anytime your initial velocity is positive, your phase angle will be negative. Okay? Well, this brings my office hours and our meeting to a conclusion. I think we got through a lot of material. Yes, that is correct. You're correct. Good job, Brian. You got it. Okay. All right. So, oh wow, I'm getting a public safety alert. All right. Well, it was great talking to all of you. Have a great rest of your day. I guess we should look forward to our last day of freedom tomorrow. Yeah, it's good luck on this week's challenge problem, and of course next week's exam. So talk to you all later. Bye.